Kia ora, Antarctic whānau. I'm Nancy Butler, and it's my great pleasure to co-chair with Flo Colleoni and Crit Fraser this mini symposium with the support of our wonderful moderator, Gabrielle Roldan and Brittany. The session, Antarctica in a Warming World, Regional Changes, Global Consequences and Future Commitments, hosts 3 invited talks by influential and inspiring speakers who are leaders in the international science community. After each talk, there will be a time for a few questions. The talks are followed then by a panel discussion, and we look forward to an exciting session. To join us for these discussions, please use the live Q&A box. Our first speaker is Professor Steve Rintoul, a Martha T. Muse recipient. Steve is a physical oceanographer who devoted his scientific career to improve our understanding of the Southern Ocean and its regional and global influence. He led the development of the Southern Ocean Observing System and served as coordinating lead author of the IPCC. Without further ado, I hand over to Steve for his presentation on what does a warming world mean for the Southern Ocean. Over to you, Steve.
Thanks very much, Nancy. I'll just try to bring up my slides here. And thanks very much to the organizers for inviting me to speak at this mini symposium and to manage to make it happen even in these very strange times. So my topic today is, what does a warming world mean for the Southern Ocean? And any discussion of the Southern Ocean and its role in the Earth system probably needs to start with the overturning circulation shown here in a very schematic way. We've been drawing pictures like this for a long time. Sverdrup in 1930 drew a very similar project, a very similar picture based on the sparse data from the discovery expeditions. But it took us another 75 years or so to really appreciate its significance in the Earth system. In this circulation where deep water rises and approaches Antarctica, water that upwells near Antarctica gets made more dense by getting cold and picking up salt underneath the formation of sea ice and sinks back down to form Antarctic bottom water, and a counter-rotating cell for the deep water that upwells a little bit further north, that moves further north again, warms and freshens, becomes lighter and sinks to supply the intermediate layers of the ocean. This is the main way that deep water that sinks in the North Atlantic gets recycled into upper layer water, so closes the global overturning circulation. And it's that global overturning circulation that really determines the important role that the oceans play in climate. The reason the ocean has stored more than 93% of the extra heat energy stored by the planet over the last 50 years is because of the overturning circulation. And the Southern Ocean is key to allowing such a circulation to exist. That window to the deep sea also allows things like carbon dioxide stored in the deep ocean to be vented to the atmosphere, which provides the key amplification that allows the orbitally driven glacial interglacial cycles to work. And it also carries nutrients from the deep ocean back, returns them to the sunlit surface layers of the ocean. So the sinking and decomposition of organic matter is relentlessly transferring nitrogen and phosphorus to the deep ocean. And the main return path is via the upwelling of deep water in the Southern Ocean. So for all these reasons, we really need to understand how the Southern Ocean overturning works and also how sensitive it might be to change in the future. So much of my talk today will focus on this overturning circulation. One guide to how the Southern Ocean may respond to further warming is how it's responded to the warming we've seen to date. So this figure is from the IPCC's recently published special report on oceans and cryosphere and a changing climate. And it summarizes the key aspects of the Southern Ocean system that we can say something about in terms of how it's changed in the instrumental period. And the main message is that the surface waters north of the circumpolar current have warmed, and the warming has been much weaker, or even cooling has been observed south of the Antarctic circumpolar current, closer to Antarctica in surface waters. The winds have strengthened. The very deepest layers, the Antarctic bottom water layer, has contracted. It's less voluminous now than it was in the early 1980s. This overturning circulation, there's some evidence that the upper cell of this, the upwelling of deep water and sinking of intermediate waters has varied with time, but there's no clear trend. It's dominated by decadal variability. And that'll be an important part of the story today. And the circumpolar current itself doesn't seem to have done a whole lot. That's really it for what we can say about how the changes have played out so far in the Southern Ocean. So why is it taking this pattern? Why is it warming more in the north, cooler in the south? Well, again, the overturning circulation is the key. And so this is another plot of observations from Armour et al. The top plot shows the storage of heat by the ocean in the southern hemisphere. And it peaks at a latitude of about 45 south. The two different curves are two different data products showing a similar result. The lower plot shows the warming trend in degrees C per decade for the same latitude interval. And you can see that surface waters near Antarctica have cooled. And the warming is really accumulating north of the circumpolar current, where the intermediate water and mode water leaves the surface and enters the ocean interior. That figure, the heat content has this shape because of the overturning circulation, where water upwells and the heat picks up heat from the atmosphere, but that heat is swept away from Antarctica. And so the overturning circulation buffers to some extent Antarctica and the southern part of the Southern Ocean from the effects of global warming, because we carry the heat away. Notably, however, you'll see that near Antarctica below the surface, there is warming. And so the same overturning circulation can bring more heat to the south, which will be an important part of Nick's talk in the second to follow mine. The overturning circulation is also important for the storage of carbon dioxide. This figure shows, again, from the SROC report, the change in inventory of anthropogenic carbon dioxide from 1994 to 2007. And you can see it's accumulating in the upper ocean, and a lot of it is accumulating in the southern hemisphere oceans. If you take the ocean south of 30 degrees south, that accounts for about half of the total ocean uptake of anthropogenic CO2. So the southern oceans are important to that. I have, as SROC did, taken a northern boundary here of 30 south. So that includes both subtropical gyre processes and the Southern Ocean itself. But again, you can see the imprint of the overturning circulation with not much accumulating near Antarctica, but lots of anthropogenic carbon dioxide accumulating north of the circumpolar current. If we look at the Southern Ocean carbon sink, so this is the net amount of carbon entering or leaving the Southern Ocean, both natural and anthropogenic. You can see that it's varied a lot over the last 30 years. So papers published in the early 2000s at the end of what's labeled the saturation period here drew attention to the fact that the Southern Ocean carbon sink was getting weaker. And because it takes up so much of the carbon that we release, this was a cause for concern. Was a signal that the Southern Ocean carbon sink was weakening. That was followed by a decade or so of rapid strengthening. The total ocean uptake of carbon is about 2 petagrams of carbon per year. So that reinvigoration period was a large contribution was a large fraction of the total ocean uptake. And then after 2012 or so, it started to reduce again. And so really the signal is dominated by this decadal variability, which is something we've only recently realized, but we still can't really explain it. Part of it is changes in the overturning circulation, but that alone doesn't seem to explain exactly why and how the Southern Ocean carbon sink varies in this way. We do need to figure it out, because about up to 40% of the variability in the atmospheric burden of CO2 can be traced to these variations in the ocean, in particular the Southern Ocean. So I've focused so far on the upper overturning cell, and that's because it's so important to sweeping heat and carbon dioxide into the ocean, and therefore controlling the Earth's response to the extra CO2 we're emitting to the atmosphere. But I now want to turn to the lower cell of the overturning circulation and Antarctic bottom water formation. And another recent and prominent discovery has been the near global extent of warming below 4,000 meters depth in the deep ocean. So red here is warming, and most of the oceans are warming. There are some exceptions. And the strongest warming is found near Antarctica, and the strongest warming of all is found in the Australian Antarctic Basin, the part of the ocean close to Antarctica, south of Australia. Also shown on this plot are the black lines on which from which the data on this plot is based on have been derived. And you can see it's actually pretty sparse. Each ocean basin might have 1 or 2 or 3 lines crossing it. And those lines are typically occupied about once per decade. So that's the information we have with which to assess deep ocean change. So we need to be a little bit careful that we're confident we're really measuring a real signal. But what we find is widespread deep warming, strongest near Antarctica. The deep waters near Antarctica have also freshened. So blue here means it's fresher over the last couple of decades than it was in previous times. And again, the strongest freshening is seen in the Australian Antarctic Basin. The SROC report, following work by Schmidtko and Ashleys, also showed that much of the ocean below 1,200 meters depth has declined in oxygen. These oxygen declines are relatively weak, but they're widespread. And they have a particular pattern which provides a clue as to what's going on in the deep ocean that can explain the warming and oxygen changes, as I'll come to in a minute. So the bottom water is warmed, freshened, and contracted, and it's a surprising climate signal because over the multiple decades over which we've seen this, it's rarely gone the other way. Most climate time series go up and down, like the carbon time series I just showed you. The bottom water warming, freshening, and contraction change, to the extent that we can observe it, seems to be more or less monotonic, but we don't really know why. What are the physical mechanisms driving the changes? Does the deflation of the densest layers reflect a slowdown of the overturning circulation or reflect a change in properties at the source? SROC suggested that it was a decrease in production. Is the trend in bottom water a natural or an anthropogenic signal? And finally, are we kidding ourselves or have we really measured something real? Is the sparse deep observing system really up to it? So I'd like to take the next few minutes to drill down and see if we're any closer to answering some of those questions. So as I've shown, the largest signals of change are in the Australian Antarctic Basin, which is also the most well ventilated. And so this plot shows the concentrations of chlorofluorocarbon 11, CFC 11, in the bottom water layer. And you can see the highest values are here in the Australian Antarctic Basin, if you can see my cursor there. And that's reflecting the inflow of bottom water formed off the Adelie Land coast, the Wilkes Land coast, and in the Ross Sea, part of which also travels west along the coast and enters this basin. If we look at what's happened in that basin, as I mentioned, for bottom water as a whole, if we look at below the layer highlighted by the yellow line on the left-hand side, which shows a density transect from Australia on the right to Antarctica on the left. That's where that density surface was in 1995, and the plots on the right show the thickness and area of that layer over time. And so over the last 40 years or so, that layer is contracted by about 50%. So the changes are big, and we need to understand exactly what's happening and what the implications of those changes are. Another figure from the same somewhat older paper shows the global work done by Sarah Perky and Greg Johnson that's really brought our attention to these changes in the deep ocean. We're based on a pretty broad brush view. Here we've taken 6 transects across the export pathway that carries bottom water north from Antarctica to the northern basins. I want to draw your attention to these histograms, the red and blue bars at each section. Near the sources, the blue bars are pointing downward and are large. That shows large freshening near the sources. The red bars show the temperature change, and there's weak warming near the sources. As we follow the path of the bottom water around the basin, the red bars get bigger and the blue bars get smaller. And so the freshening is strongest near the bottom water sources and warmer downstream. That's our second clue about what's driving these changes. The third clue comes from looking at oxygen levels in the deep ocean. So this shows oxygen at 4 times along the same section that I showed you, the density transect 4. And oxygen's on the x-axis. And particularly if you focus on the red, green, and black curves, the changes from 1995 to 2005 to 2012, the oxygen concentration in the deep ocean hasn't changed very much. So the ocean's still getting ventilated at about the same rate, that suggests. But the curves are shifting up on this plot, corresponding to the oxygen maximum appearing at lighter and lighter layers as the densest layers have disappeared or shrunk in volume. And so the message is that we're still apparently ventilating the deep ocean, but on lighter density surfaces. And I won't show it to you here, but those lighter surfaces have also inflated in volume as the dense surfaces have deflated. So that's the next clue. Finally, I want to turn to the Ross Sea. The longest time series we have of water properties relevant to bottom water formation comes from the inner part of the Ross Sea, thanks to Stan Jacobs. And over 50 years, again, there was a pretty monotonic freshening trend and a large trend. So freshening at about 0.03 per decade on the shelf, which is a large value in terms of global salinity changes in the global ocean. And that freshening trend was attributed to meltwater input from the Amundsen Sea, which was big enough to explain the freshening trend and trends in oxygen 18 over the Ross Sea shelf. But it was more of a consistency argument than a quantitative demonstration, that there was just enough meltwater coming in to explain it. But we didn't know much about how it got there or what other processes might be involved. So it was surprising, therefore, when Italian colleagues working in Terra Nova Bay noticed that after 2014, that long-term trend that they had also seen, covered here in the first 20 years of this record, abruptly shifted towards saltier values again, shown in this the red curve here, where from Terra Nova Bay, where the saltiest shelf water is found in the Ross Sea. And that salty shelf water is the precursor to Antarctic bottom water formation. So after 2014, the salinity increased and it returned to values typical of the 1990s. So this is happening at a rate that's about 5 times, the salinification was at a rate about 5 times greater than the freshening trend seen in the previous couple of decades. So this paper showed this signal very clearly, but we were not able to explain the causes of the increase in salinity after such a long period of freshening. So I'd like to touch on that now and talk about some work led by a brilliant young Italian researcher, Alessandro Silvano, who's now at the National Oceanography Center in Southampton. So we're going to focus on the Ross Sea shelf, shown here, and measurements made off Cape Adair and at 150 East. If you can see those plots on the lower left, these are temperature salinity plots on the left from Cape Adair and on the right from 150 East. Let's focus on the Cape Adair section. The black curves, if I can get my cursor back, are from 1969 to 71. The next occupation was much fresher in 1992, the red line. Much fresher again in 2011, the yellow gold line. And in 2018, when we went back in the ship, it had rebounded to saltier values. Similar signal is seen at 150 East. And if we look at the salinity of the bottom water, the density of the bottom water, or the thickness of the bottom water layer, it tended to decrease up until about 2010 or so and then rapidly rebound. So that's a signal that the shelf water changes are getting into the deep ocean and affecting Ross Sea bottom water. So why might that be? Well, the first place you might look is to sea ice production. And indeed, the salinity of the dense shelf water is correlated with sea ice production. More salt, more brine release, saltier shelf water. That's not really a surprise. But it is, or at least was to me, a bit of a surprise that it's also highly, that the sea ice production in turn seems to be linked to reduced sea ice inflow from the Amundsen Sea. So the less sea ice we get flowing in, the more sea ice is formed. So what's the mechanism? The idea is that less sea ice flowing into the Ross Sea reduces the concentration of sea ice on the Ross Sea shelf. And that allows more open water, more rapid ice formation, and more brine release. So that reduced sea ice inflow preconditions the Ross Sea shelf to form more sea ice. So what led to weaker inflow? Well, if you look at the inflow to the Ross Sea here on the eastern side of the shelf, in 2015 to 2018, the wind anomalies were westerly, towards the east. And the sea ice concentrations were anomalously low, shown in the red colors. And the sea ice anomaly, concentration anomaly over the Ross Sea, entire Ross Sea shelf, shown in the black in the lower plot, and the easterly winds in the gateway entering the Ross Sea are again highly correlated in the sense that where the weaker the easterly winds, the lower the sea ice concentration anomaly in the Ross Sea. So we keep working back the chain. So then you say, well, what caused the change in the winds? What was different about the period between 2015 and 2018 was that there was an unusual combination, so unusual in the instrumental record, of persistent positive SAM over a number of years and a very strong El Nino event. So the black, in the upper left plot, the black curve shows the summer SAM index anomaly in the summer SAM index. And the red curve is the Southern Oscillation Index anomaly, a measure of El Nino. Negative values correspond to El Nino events. The plots on the right show how the winds are affected. Both those factors, positive SAM and negative SOI, tend to drive eastward wind anomalies over the entrance to the Ross Sea shelf in this region. And so the story is a 5-step process. So what drove the rebound of Ross Sea bottom water formation? First, the unusual coincidence of positive SAM and El Nino over a number of years. Those drove weakened easterly winds that reduced the import of sea ice to the Ross Sea. That in turn increased sea ice formation on the shelf in the Ross Sea, producing saltier, dense shelf water, the precursor to bottom water. And that made its way off the shelf ultimately and increased the salinity, density, and thickness of the bottom water layer. And so what should we take home from this story? The first is that this doesn't say that the freshening is unrelated to melt. It still looks like there's good evidence that the multi-decadal freshening trend in the Ross Sea is driven by increasing glacial melt in the Amundsen. But it does show that episodic sea ice anomalies driven by climate modes can drive variability on top of that trend, and it can be much stronger than the trend itself. The key thing is the freshwater balance of shelf waters, and that's really something that we don't know much about. It's complicated. It depends on interaction of the ocean with the atmosphere, including remote teleconnections, as I showed, sea ice, icebergs, ice shelves, etc. It also illustrates the connectivity between different parts of the shelf, and that's something we really don't know much about yet. We need better measurements on the continental shelf, including through winter, to know how one region is connected to another. There's some suggestion that these conditions, positive SAM and strong El Nino, might become more frequent in a warmer world, and that would increase the opportunity for sea ice to counter the effects of increased glacial melt. I want to touch quickly on one other, you can think of that superposition, that coincidence of positive SAM and strong El Nino as a natural experiment. Another natural experiment occurred when the Mertz Glacier Tongue calved. The Mertz Glacier Tongue, in the lee of the Mertz Glacier Tongue was a strong polynya shown in the dark colors here, where dense water was formed to form that was the source of the Adélie Land bottom water. And that flowed out through this deep depression and through a sill out to the deep ocean. In 2010, the Glacier Tongue calved, and as a result, the polynya became much smaller, much weaker, and much of the area filled in with sea ice. So that was a bit of a hammer blow to sea ice production shown here. So the calving event in 2010 reduced the net sea ice formation in the region by about half. And we happen to have moorings at the sill 4 years of record prior to the calving event and 4 years after the calving event. And if you focus on the black lines in these plot, you see a strong seasonal cycle with the strongest export at the end of winter. The black lines are all from the same depth, both pre and post calving. But you can see that post calving, the densest water that we see here, these peaks in the black line, are only as dense as the lightest water we saw in summer in the prior to calving. So the calving event did have a major impact. So this natural experiment is another illustration of the sensitivity of bottom water formation to what happens on the shelf. So to sum up, first, the clues that I've tried to reveal to the causes of bottom water change include that the largest changes are observed in the Indian Pacific. The freshening is stronger near the source, and the warming and oxygen decline are stronger downstream. The densest layers have disappeared and isopycnals have descended. The lighter classes of bottom water have inflated and increased in oxygen. And if we change the dense shelf water salinity, either by reducing it after the Mertz calving or increasing it due to sea ice formation in the Ross Sea, we inflate or deflate the bottom water layer. And so to get back to our 4 questions, what are the physical mechanisms driving changes in bottom water? The key is the freshening of the source waters. Lighter dense shelf water means lighter bottom water. That's not a big surprise. But the loss of those densest layers causes isopycnals to descend, to get deeper. That immediately causes warming. That means warmer water descends as well on those lighter isopycnals, causing warming at any given pressure surface. Very important also is the fact that at the sills connecting basins where water flows from one basin to the next, as those isopycnals descend and cause warming at the depth of the sill, only that warm water can now reach the basin to the north. So we get warming to the north as a result of that sill effect and the descent of isopycnals to the south. So the long-term trend is likely driven by increased glacial melt, but there's variability in that trend that can be driven by sea ice processes. Is it a slowdown in the overturning circulation? My reading of the evidence is that it's probably not, that it's inflation and oxygen increase in the less dense layers suggests that we're continuing to ventilate the deep ocean, but at lighter layers, but continuing to pump oxygen into the deep ocean. Is this trend a natural or anthropogenic signal? This is a difficult question. But the multi-decadal trend in bottom water properties has been linked to an increase in mass loss from the West Antarctic ice shelf. That loss in turn has at least now tentatively been attributed to anthropogenic forcing, modulated by internal climate modes and ocean ice feedbacks. And I suspect Nick will tell you more about that in a minute. Does the sparse deep observing system resolve variations in bottom water? Well, it's clear that decadal repeat sections would alias variability driven by climate anomalies and episodic events, as I've shown. Deep Argo will help, but we need to expand that system to really be able to measure how and why the bottom water is changing. So finally, to bring us back to what a warming world means for the Southern Ocean, we'll see more warming stronger in the north as a result of the overturning circulation, freshening as a result of increased precipitation and increased ice melt, and ongoing acidification. The westerlies are important. They drive much of the Southern Ocean circulation, and they're projected to strengthen, but it will be a battle between greenhouse forcing and repair of the ozone hole over the coming decades. And so the strengthening trend will emerge once greenhouse forcing has become dominant. That will take some decades to happen. Those changes in wind will likely drive changes in the circulation, either the overturning circulation on circumpolar scales, but also local effects to do with that can explain changes in the regional changes in sea ice expansion or decline, as many authors have described, or as local changes in winds that can affect the sea ice transport that I talked about, or the on-shelf transport of warm water to affect ice shelf melt. If changes in the overturning circulation did happen, they'd impact the ability of the Southern Ocean to take up heat and carbon, but we're not really in a position yet to assess the likelihood and magnitude of future change. There's still persistent biases in climate models that prevent us from doing that very well. And finally, the most important change might be changes in ocean heat transport to ice shelf cavities and the consequences for sea level rise. But our understanding of those processes regulating basal melt remain incomplete. So I'll leave it there. Thank you very much.
Thank you, Steve, for this wonderful, comprehensive talk and leading us through some very complex arguments to understand for us all the reasoning behind your conclusions. We have time for one question, and I'm just choosing one from the list that is quite relevant to your talk right now. It was asked, is it also possible that sea ice transport into the Ross Sea embayment could be due to changes in the Ross Sea gyre, not just wind?
So it is possible. The currents that are flowing, that are bringing sea ice onto the shelf itself are the slope current running along the shelf break to some extent, but also the flow on the continental shelf itself. I guess I'd expect the flow on the continental shelf maybe to be less related to the gyre. But the slope current on the shelf break is the southern boundary of the Ross Gyre. That may have also responded to changes in the winds, but I suspect that those that the key really is what's happening on the shelf, and so that the sea ice carried by those currents on the shelf can enter, or that are windblown directly, can get up on the continental shelf itself and not be limited to the shelf break.
Thank you, Steve.
Thank you, Steve. Our next speaker is Nicholas Golage. So Nick is an associate professor in the Antarctic Research Center in Victoria University in Wellington. He's specialist in the numerical simulation of Greenland and Antarctic ice sheets and their response to changing external and climate forcing over time. His most recent work has focused largely on policy-relevant timescales and societally relevant questions, such as future ice sheet contributions to global mean sea level changes. Nick currently holds a Royal Society of New Zealand Rutherford Discovery Fellowship, and he is a lead author of the 6th assessment report of the IPCC and co-leads of the Future Projection Expert Group of the Antarctic Science Platform. Nick, over to you now.
Right, thank you, Flo, for that very flattering introduction, and thanks to Crit and Nancy for as well for pulling this mini symposium together. It's really great to have these talks online like this, and thanks to everyone for tuning in, and for the SCAR organizers for making all this happen. I mean, it's a topsy-turvy world at the moment, so it's great that this can go ahead. Yeah, thanks to everybody for coming online. I mean, I know everyone's kind of tuning in from different places around the world, and some people probably just want to go to bed. So really appreciate that engagement. It's really nice to see. It's great to see 200 people listening in. So that's awesome. I'll just pull up some slides. I guess my final thanks really is to Steve for giving not just a very interesting, but a very beautifully presented talk that covers a lot of the really fundamental stuff that we need to know when it comes to thinking about the ice sheet response to future warming. So hopefully you can all see there my title slide, and hopefully they'll all come through. Let me go. Right, okay. So in a very simple form, this is sort of almost insulting compared to what Steve's just told us about the ocean, but as glaciologists, we like to have a reduced view of the complex world in the ocean, and this is just a very simple representation from one of Eric Grignot's papers last year. There are other studies out there, of course, but what we're seeing here is, on the left-hand side, the pattern of mass loss from the Antarctic continent. And of course, we're all quite familiar with these numbers, and some pretty scary numbers coming out of West Antarctica there, the very large circles. And we've been seeing that pattern for a couple of decades. More recently, we're seeing mass loss from East Antarctica, particularly from the Totten Glacier. So there's some concern there. The Totten and Denman Glacier both have the potential to really stir things up a little bit. So that's kind of the state of play as far as we can tell within the uncertainties. And it's kind of clear that when we look at the map of ocean temperatures, we can see that it's not just about where the warm water is in terms of the Southern Ocean pattern, but it's really about where that warm water is getting up onto the continental shelf. And there are only a few places where it's managing, where those orange and red colors are sort of managing to breach that blue protective ribbon of cold water around the continent. So there's a number of feedbacks involved, which we'll come on to. But basically, the more we can do to maintain that blue ribbon, the better things are for the ice sheet. Now, excuse me, Steve sort of talked about some of the changes happening within the water masses around Antarctica. One thing that we like to do when we run ice sheet projections, of course, is we simplify things and run coarse resolution models to get some sense of change over large areas and long periods of time. And when we do that sort of thing, we consistently see in the models quite a characteristic pattern where, as we warm the Southern Ocean and we bring that warm water up against the ice sheet, we produce the melt that Steve mentioned. And in some cases, that can lead to a melt layer basically floating on the surface of the ocean, and essentially leading to a sort of stratification of the continental shelf waters, which by bending those isopycnals can, under certain circumstances, encourage more of that warm water. Instead of ventilating to the surface and losing the heat, it tends to sort of dive further back into those ice shelf cavities and promote further melting. And we think that there's the potential for a positive feedback mechanism there. So the warm water basically generates melt that in turn accelerates its own melt. So it's potentially an important problem. We've looked at it with a range of different models, but I'd say that it's still far from clear as to whether this is a process that's widespread at the moment, whether it's going to be important in the future, something that really needs to be looked at further. On the right-hand side there, I'm just showing some anomalies for different sort of climate variables when you do put that cold meltwater into the, particularly in the Amundsen Sea area, driven by melting of the ice sheet. We can see from top to bottom air temperature anomalies, sea surface temperature anomalies in the middle, and then subsurface temperature anomalies at the bottom. So this is just the consequence of the meltwater basically leads to a reduction in air temperature, surface, sea surface temperatures, but it leads to a warming in those sort of mid-depth layers. Now, when it comes to the atmosphere, it's a bit more sort of tricky to see what's going on. I mean, we have, Steve mentioned SAM and El Nino, and of course in 2016 we had this big El Nino that led to widespread melt over a large part of the Ross Ice Shelf. And that was kind of unusual because we don't really see a whole lot of surface melting in Antarctica. We do see it in parts of the Antarctic Peninsula, of course, but when we come to sort of the continental area, it's kind of unusual. So seeing this kind of melt event that lasted for a couple of weeks, this is pretty significant. So if that's likely to change in the future, that could potentially have some impact on the mass balance total for the continent. Simulations have been done, of course, with models of varying complexity. The one I'm showing here, top right, is from Luke Trussell's work from a few years ago now, but a very nice study basically showing that the path we follow in terms of the emissions trajectory following RCP 4.5 versus 8.5 in this example really does lead to quite significant differences in the melt that's likely to occur. And of course, we're probably familiar with the idea that increasing surface melt, particularly over ice shelves, has the potential to enhance the calving rate of those shelves, and in some cases perhaps lead to widespread collapse of those shelves. Now, when it comes to the other part of the atmospheric forcing, we have to think about the accumulation. We're not just sort of melting ice, but we're obviously accumulating snow in certain areas. Very difficult to measure, partly because it's hard to get a gauge on what's falling, and then it has the problem that it tends to blow around. So some nice work here from Alex Gossart, who's been doing a lot of work on blowing snow and trying to build that into the models so that we actually get a much better representation of where the snow is actually accumulating after it falls. Now, we get a really good handle on those accumulation patterns when we look at the longer term records, because this example here in the bottom right from Medley and Thomas, just showing the centennial scale trend of accumulation in different parts of the continent. And generally, basically, it's kind of good news in the sense that the rate of accumulation is increasing. So there is more mass falling on the continent, and that's good news, obviously, because it's it's related to warmer air masses bringing more moisture, and it offsets some of that mass loss that we know is occurring. Unfortunately, the numbers involved are still too small to completely offset the mass loss, so we're left in a state of negative balance. But interesting work to be done there to see how all that evolves in the future. Now, when we come to think about the future evolution under those different forcings, ocean and atmosphere, we really have a sort of tale of two ice sheets here, because Antarctica responds obviously very much to ocean forcing, and we can see there the figure on the sort of lower right hand side, the marine ice sheet instability. This is a concept that's familiar to many of you, I'm sure, but essentially the idea being that when we put warm water against the ice sheet, it starts to retreat. And if that retreat occurs in an area where the bed of the ice sheet is actually sloping down towards the interior, then you have a self-sustaining retreat of that sector, and you basically lose more ice than the forcing alone would give you. Now, in Greenland and Northern Hemisphere terrestrial ice sheets in the past, like the Laurentide in that top right-hand figure there, they behave somewhat differently. They're still driven by dynamic responses to forcings, but a large part of their balance is controlled by the atmospheric conditions. And we have an instability mechanism there as well, which is the elevation surface mass balance feedback. So basically, as the surface mass balance either reduces or gets more negative, then obviously the surface lowers. And as it does so, it lowers itself into warmer air masses because of the lapse rate. And so that accelerates melting or reduces accumulation. And you get this runaway feedback that over centuries to millennia can basically destroy an ice sheet depending on the temperature forcing that's applied. So, we have a pretty good understanding of those kind of instability mechanisms and the way that they affect ice sheets differently. But it's really hard to understand the point at which these things are triggered. So some nice work by Frank Patton, when was that, a year or two ago, pulling together basically the sort of the available evidence, and a lot of it comes from modeling experiments. It draws on future simulations and simulations of past ice sheet extent, and really trying to sort of narrow this window of what is the point when irreversible loss of the ice sheets really starts. It's a difficult thing, but basically it looks like that 1.5 to 2 degree window is kind of the point where these instability mechanisms can lead to ongoing self-sustained changes. So that's kind of a real alarm bell when we think about the Paris Agreement, when we think about the NDCs, the nationally determined contributions that each country is making to reduce emissions. We're still actually looking at warming of around sort of 3 to 3.5 degrees by the end of the century. So some concerns there about how that's going to play out. Now, of course, different parts of the Earth system respond differently to warming, and the ice sheets and mountain glaciers contribute to sea level rise at different times and at different rates. So there's quite an old figure here on the left-hand side from the AR5 IPCC report, basically showing you that in the short term, basically most of the sea level rise signal that we can measure is coming from that sort of immediate thermal expansion of the ocean. That's the sort of pale blue line in that figure. But very quickly, mountain glaciers start to contribute more as a proportion. They start to melt, obviously, under warmer air temperatures. But the ice sheet contributions, the dark blue line for Antarctica and the green line for the Greenland ice sheet, they take somewhat longer to contribute. But of course, they keep going when the others are declining. And we've learned a lot, I think, since AR5 about the style of response of those two ice sheets. And I'll come on to that a bit later. But the bottom line is that basically these things, all these elements contribute at different times over different time frames. And if you're a policymaker, that makes things quite difficult because you start having to think about the time frame that you're interested in for designing your policy or your mitigation and adaptation measures. And the figure on the right-hand side there is really a schematic that's kind of showing just how different factors, those kind of vertical boxes, become important at different times. So if you're looking sort of 10 to 50 years ahead, actually you don't really see much scenario dependence between the projections of sort of mass loss from the ice sheets in particular. But as you go to longer timescales, you see those scenarios diverging. You'll see that, for example, the West Antarctic ice sheet, here we've got a West Antarctic collapse in the red box at the top, but then by the second row down, it's moved into the gray boxes. So it's become part of that long tail. And this long tail of the upper end of sea level rise is something that causes a lot of concern because we don't really understand the processes that basically lead to this long tail. So that's kind of some scene setting, but I thought it'd be useful to kind of recap where we're at in terms of projections. It's interesting to sort of go back less than 10 years to AR5 and think about the state of knowledge in terms of ice sheet projections. At that time, we had plenty of ice sheet models and we had a few sort of projections for the future, but they were quite often done in fairly arbitrary ways in the sense that they were using a sort of, a step change forcing in CO2 or ramped forcing or just a doubling of CO2. They weren't tied to a particular scenario so much. The physics that was incorporated in the models at that stage maybe isn't as advanced as what we have now. And so we weren't really capturing dynamic responses as well as we really needed to. And I guess that kind of led to this problem in AR5 where essentially the ice sheet's contributions based on mass balance changes alone could be sort of reasonably well quantified. But the dynamic contribution, this potential for sort of runaway loss, couldn't be quantified. It couldn't be assessed very well. And because of that, it meant that a number was put in that was kind of considered a best estimate. But at that stage, it was very unsure as to whether there was a scenario dependence to that dynamic contribution. And if there is, then how would it even be defined? So for that reason, there was no scenario dependence assigned to those dynamic values. At that time, there was a big call to the community, of course, saying, can we have better ice sheet models? We need things that can capture these dynamic processes. We need to better refine that term in particular. And of course, that led to a flurry of activity. And by 2019, when the special report on climate and cryosphere was published, there were a few more models available. But still, there were very few that had actually run scenario-based simulations. So ones where they're actually using a present day state that looks like the present day and then uses an RCP scenario from the IPCC that actually relates future changes to a particular pathway of emissions. There were a few studies around, and these are basically the ones that were used in SROC for some, if not all, of the RCP scenarios. There's some problems, of course, because we went through that period of transition from the SRES scenarios to RCPs. They're not always entirely sort of interchangeable, so there's some problems kind of understanding how one relates to the other. But I guess the take home from this really is that there's even allowing for the uncertainties in each of those panels, there is some greater sense of scenario dependence in the outcomes. And you can also see that the SROC put slightly higher estimates for for RCP 8.5, moving both the upper and lower tails of that distribution. Still lots of work to be done though, and this triggered a response from the community over the last few years to basically pull together all the modeling groups or lots of the modeling groups around the world to use a standardized approach, the kind of CMIP protocol that's worked very, very, very well for the climate and ocean modeling community for many years, and to do these scenario-based simulations in a consistent and standardized way. So ISMIP kicked off a few years ago with an initialization phase to make sure the models could accurately represent not just the state of the two ice sheets, but also their evolution and their response to different forcings. And those results are actually now getting published. So it's really nice to see the results from the prognostic simulations coming through now. This is from the Greenland paper that's just been published. And we can see basically that there's quite a clear scenario dependence. If we look at the graph there on the left-hand side, when we think about the way that Greenland will respond to future warming, it's pretty clear that the more we warm the atmosphere and ocean, the more we're going to lose from the Greenland ice sheet. There is some dependence on the GCM that's used and the sort of way that the emissions scenario turns into a sort of temperature forcing. But basically, it's pretty clear that under the RCP 8.5 scenario, we're probably going to get something like 10 centimeters out of Greenland, which is actually remarkably consistent with many of the studies that have come out over at least the last 5 years, either from climate models alone or from coupled climate and ice sheet models, or even just standalone ice sheet models. They're all very consistent. There are some that are slightly higher. But they're showing basically the same pattern of mass loss. And you can see there in the map on the right-hand side that the dark blue areas are the areas where under that 8.5 scenario, that's the areas where you'd get the most thinning by 2100. And it's no surprise that it's following those, the pattern of those big outlet glaciers like Helheim and Jakobshavn. Now, it's a very different story when we come to Antarctica. Many of the same models and modeling groups contributed to the Antarctic simulations for ISMIP 6. But we have different problems. You know, a lot comes down to the ocean. We hear a lot about the ocean. We've talked about it a lot already. It's not just a question of how much the ocean is warming, but it's a question of how we deal with the physics that dictates how that ocean forcing turns into an ice sheet response. It's a complicated process. It's somewhat more complicated than just the top-down melting that really dominates something like the Greenland ice sheet. And because of this, we end up with quite a spread in the model projections. So looking at the population of projections here, we can see that there's a range of future contributions, anywhere from basically 30 centimeter contribution under 8.5 to actually a -7 contribution. Basically, the Antarctic ice has increased in mass. So there's still a lot of work to do in terms of understanding both the forcings that are going into driving these models, but also into gauging kind of how those models are responding to those forcings. What's kind of most concerning, I suppose, is that when we look at the maps there on the right-hand side, the lower panel, the top one's showing the sort of thickness change, I think from the sort of ensemble. The lower one shows that standard deviation. So it's showing you basically where the different model members differ most. And it's sort of concerning that the biggest differences are in the areas of greatest present mass loss, so the Amundsen Sea embayment, of course, and around the Totten and Denman glaciers. It's no surprise, of course. I mean, these are the areas that are thinning most, and so those are the areas that are most dynamic. So depending on how the models capture those dynamics, you can get very different outcomes in your projections. So we've made a lot of advances, but there's still a lot of work to be done. There's different approaches can be also useful. It's not all about ISMIP. There are other ways that we can kind of get a handle on what the future contribution of the ice sheet might be. On the left-hand side here, we're looking at the magnitude of sea level contribution from the Antarctic ice sheet by 2100 under 4 different RCP scenarios from this LARMIP2 study led by Anders Lieberman, which basically uses a linear response function. So we're basically treating it in a more conceptual way, but actually still using the sort of the dynamics of the system. What's interesting here is that we do see some scenario dependence in the upper tails of those magnitude plots. But when you look at the thin white lines, the medians, they're actually very, very consistent. There's not a whole lot of change going on. So you could say, well, either that's good or bad, depending on your point of view. But what's more telling is that when you look at the rates, which is the panels shown on the right-hand side, this is probably what's more important if you're a planner or a politician. Even if the median of the magnitude of sea level contribution shows little scenario dependence, the rate of change by the end of the century is very different. So if we look at the rate of change by 2100 under a 2.6 scenario, it's only about half what it is under an 8.5 scenario. So that's pretty important if you're trying to plan for future adaptation. So we need to think, I guess, more about the tendency of these contributions rather than the magnitude. We do get a bit hung up on magnitude sometimes. Now, looking further ahead, again, we can do a sort of conceptual type experiment. We can think about, what happens if some really crazy things happen? What happens if we lose some of the big ice shelves? This is a really nice study led by Frank Patton and Sainan Sun, where basically they got modeling groups to ask this question of what if we lose the ice shelves. So we run these experiments where we basically just take out the ice shelves either immediately or we melt them very, very quickly. So trying to capture a range of responses. And we then let the models run for 500 years and see what those longer term responses are. And it's pretty clear that actually models are quite consistent. The bottom line here is that if we lose the ice shelves, we lose West Antarctica. That's the take-home message. Now, the models differ in terms of how quickly that will happen, but it seems to be a fairly consistent pattern. Is there a role for single model studies, or is it all about multi-model intercomparisons? I think personally we still need to do single model studies, and I'm keen on this because I think it allows us to take a consistent approach to studying the 2 ice sheets in the same framework. And this is what we did over the last couple of years, looking at Greenland and Antarctica in the same framework, using the same CMIP forcings. And they're valuable, these kind of studies, because it tells you something about the way the ice sheets differ. And here you can see, even if you just look at the bottom right-hand panel there, you can see that the Antarctic contribution accelerates through time as those dynamic feedbacks kick in, whereas the Greenland contribution basically is quite linear. It basically follows the mass balance forcing. The dynamic response in Greenland essentially becomes quite self-limiting. When we try and map that out and compare the 2 ice sheets, we can see that even more clearly. In Antarctica, you'll see a lot of those dark blue histogram bars, and the areas where you're seeing the largest of those dark blue bars are coincident with the areas where you're seeing the yellow bars too. And that's basically showing you that most of the mass loss is coming from the basal melting of ice shelves. And there's a bit of brown in some of those areas, particularly in the Amundsen Sea sector on the far left-hand side. So it's a dynamic response to that thinning that's driving most of the sea level contribution by 2100. In Greenland, we see a very different pattern. We see most of the mass loss coming from the pale blue bars. So that's the surface mass balance. And actually the dynamic losses tend to tail off over time. What does that mean? Again, we come back to this environmental impacts that we started with. It's not just about changing the temperatures of the ocean and affecting the ocean circulation, but we can see from quite a few studies that the more we warm the globe and more meltwater we put into the North Atlantic, the more likely we are to see a reduction or even collapse of the Atlantic meridional overturning circulation, which obviously dictates a large part of the heat transfer around the globe. And it also upsets precipitation patterns by putting all this meltwater into the ocean. So widespread impacts that we're only really beginning to kind of understand. And this is really where the next phase of research would be going and is going, looking at how these responses play out in fully coupled climate ocean ice sheet models. A couple of final points here. We need to think beyond the 2100 timeframe. A couple of real simple experiments here, Greenland and Antarctica in these sort of in these plots. In the top panel here, you can see basically 4 lines, different colors. These are stabilization timeframes. So the black line is if we stabilize climate at 2100 values under RCP 8.5. The brown is stabilizing at 2050. The light blue is stabilizing at 2020. And the dark blue line is stabilizing at a present, well, not a present day, a year 2000 notional present day state. And you can see that the volume loss for both Antarctica and Greenland just keeps increasing through time. The reason for this is actually different. And again, it comes down to the different drivers affecting these ice sheets. In Greenland, you can see that surface mass balance, despite only being forced for 100 years and then held constant, or actually less in the stabilization scenarios, we see this sort of forced window in the gray shading, but then the surface mass balance stays very negative. So Greenland basically just keeps responding to that negative mass balance and keeps losing mass. The subshelf mass balance, the basal melting, actually sort of peaks and declines because obviously as you warm the waters, you melt the ice that's floating there, that tends to retreat. And as the ice sheet contracts, it loses that connection to the ocean. So the ocean forcing the subshelf mass balance basically sort of drops off. Completely the opposite really in Antarctica. We see a peak in the surface mass balance sort of relatively early on because of that warmer air bringing in more precipitation. And then the sort of integrated mass balance drops off because essentially as the ice sheet loses mass through dynamic thinning and ocean forced retreat, the surface area diminishes. And of course, the big driver, the bottom right panel there for Antarctica is this ocean heat. So regardless of when you stabilize, the heat is in the ocean and you're going to keep melting the ice shelves. Okay, I've gone a minute or so over time. A couple of take-home messages there. And the bottom line really is that we know the 2 ice sheets are both very sensitive to only a small amount of warming. So that's something we really need to take quite seriously. The greatest threat, excuse me, is probably going to be the dynamic response of the Antarctic ice sheet. We don't really know what's in store until it plays out, and that's something that models are really grappling with at the moment. And the sobering thought really is that, yeah, we can't really kid ourselves that we can prevent the global consequences of ice sheet melting because they've already started. We're already seeing those consequences. But what we can do is reduce the magnitude of those impacts. And that's the reason that we need to go really hard on the mitigation. I'll leave it there and take questions at this time. Thanks.
Thank you very much, Tim, Nick, for the great talk and very informative about the state of Antarctica and Greenland relative to projections and probability. So there is a couple of questions that aim toward the same direction. Effectively, you showed us a lot what will happen by the end of the 21st century. There are a couple of questions that ask how the model perform beyond that window. Actually, could you address that?
Yeah, no, it's a really important question, and it's something that is actually quite hard to answer because not many. Well, we have 2 problems. There aren't many long scenario forced runs for CMIP models for a start. There are some extended runs that go to 2300, but not as many model groups run those extended simulations. So in terms of the forcings, we have fewer climate model outputs to work with. And of course, from the ice sheet perspective, even if we have those forcings, what we find is that the differences in the way that the models respond to those forcings, and the way they deal with the dynamic responses, particularly in Antarctica, where we've got marine ice sheet instability and other things to account for. What we find is that the further ahead we look, the more the models tend to diverge, but they're consistent in the sense that pretty much all models for multi-century to millennial timeframes project multi-meter contributions to sea level. What they differ in is the exact magnitude of that multi-meter contribution, but I think it's still alarming enough that we're genuinely looking at that kind of scale of sea level change.
Thank you very much, Nick. There are other questions, but we will probably answer to those questions during the panel discussion, so I think we can proceed.
Okay, it gives me great pleasure now to introduce Stephen Chown, who probably needs no introduction. We all know him as the president of the Scientific Committee for Antarctic Research. And Stephen is, of course, also a stellar researcher in his own right. He's published hundreds of papers, amassing an astonishing more than 31,000 citations with an H index of 91. He's got very diverse research interests, publishes across a range of fields, and is particularly interested in invertebrate physiology and ecology. And he has a very strong focus on Antarctic and subantarctic ecosystems and conservation. In 2009, he was awarded the Tinker Muse Prize for Science and Policy in Antarctica. In 2014, he was awarded the SCAR Medal for Excellence in Antarctic Research. And this year, he was elected a member of the American Academy of Arts and Sciences. As well as being president for SCAR, he's also just started a role as leader of a major new Australian Research Council funded program, securing Antarctica's environmental future. So without further ado, I hand over to Stephen to talk about Antarctic biodiversity responses to a warming world.
Thank you, Crid. Thank you very much for the invitation, Nancy, Florence, and Crid, to join this session and present the final talk that has to do with, of course, the responses of life to the situation that's unfolding in front of us. What I'd like to do today is speak to you about Antarctic biodiversity responses to a warming world. And biodiversity, of course, is crucial in many ways. And I think more than ever, we're realizing that at the moment, since just a small change in biodiversity has essentially forced us to do our business in a completely different way with the coronavirus pandemic. Biodiversity is, of course, also important because it really forms the basis for our societal future. We are reliant, of course, entirely on the resources that life brings to us. So understanding biodiversity responses is crucial. What I'd like to do in the talk today is deal with just a few issues. I'm not going to go for a comprehensive synthesis of what we understand the effects are of changing environments, as we've just heard described so eloquently by both Nick and Steve. I'm just going to pick out a few examples, and I'm going to do so for an important reason. And that reason relates also to one of the slides that Steve Rintoul showed. And that is, just as we have few tracks across the Southern Ocean to understand what water masses are doing, there are actually very few long-term studies of change in Antarctic biodiversity. One can name some of the famous ones, the LTR studies at Palma and in the dry valleys by the US, the French Polar Program studies of birds on the Southern Ocean islands, some Australian work in East Antarctica. But the time series, the long time series, are quite few for the region. And I think at the moment there's a real danger that we're going to see gaps appear in those time series. And so for those who are responsible for national polar programs, we know there's a great deal of risk management to be done to ensure that that small piece of biodiversity, the coronavirus, doesn't reach Antarctica. At the same time, that has to be balanced against the knowledge we'll gain on how things are changing and what we might expect into the future. So I'm going to deal with just a few examples, and I'm going to start with theory because I think it's important for us to remember that theory underpins all understanding and prediction. And amongst the diversity of theory available, one that suits us very well in this context is Mark Wieland's theory of communities. And essentially, we're talking about just a few simple processes that are important in biology. Speciation, where species change and evolve either unrecognizably or split into two. Selection, which is the result of changing conditions. So for example, we think of temperature changes in Antarctica a great deal, or of course at the moment, the arrival of a new virus. There's drift, which is basically just stuff happens. It's stochasticity. And dispersal, with movements of individuals from one area to another. And if we think about this underlying theory, it helps us actually to understand what the basis is of the change we might see, and also helps us crucially to understand where attribution might lie. So just as the previous speakers have indicated the complexities with attribution in the physical world, there's some complexities of attribution to causes in the living world too. Often when I present the scheme that was developed very elegantly by Mark Wieland and later by colleagues of his, people ask, where's extinction, since that's such a large process and it weighs uppermost often in biodiversity conservation thoughts. And extinction is actually here, but extinction is the result or the outcome of these other processes. So locally, some population might be extirpated simply because all the individuals move. Whereas globally, of course, it's a response to selection. In other words, organisms might not be able to deal with the environments in their narrow range, or there may just be a stochastic accident that leads to their extinction. And as I go through the examples with you today, I want you to bear in mind and just think about how these processes operate and which of them may have led to the situation we see. We've just had two really good talks on the physical changes. I'm not going to go back through them, but I would just like to remind those listening in that from a biodiversity perspective, we think about marine pelagic biodiversity, marine benthic biodiversity, and terrestrial biodiversity. And all of these changes, ocean warming, sea ice changes, ice mass declines, and of course, atmospheric and surface warming are important and are worth considering. So from a life sciences perspective, we have to rely on our colleagues in the physical sciences to let us know about what the changes are, and of course to help us with attributions. And in turn, we can feed back to them to explain what we're seeing. So for example, some work by Jan Struggle and colleagues a little while ago just showed how important genomics is for perhaps understanding past changes in marine-based ice sheets. Having borne that in mind, let's start with just a few examples from marine systems. And it gives me a great deal of pleasure really to refer to work by colleagues from around the globe, hence the SCAR logo I put on the front of the slides. So the first piece of work I'd like to deal with is some work by Angus Atkinson and colleagues on krill, a very important component of Antarctic and Southern Ocean food webs. Before the treaty came into force, so in the early 1900s, we found that krill was in the Scotia Arc area, had its distribution around South Georgia and a little further south. And over time, there was a small movement. By the time CAMELAR came into force in the 1980s, there was already a move to the Western Antarctic Peninsula. And now over the past 2 decades, we see quite a substantial move. Everyone will appreciate the importance of krill in food webs, and these changes are really important to consider and what they may mean for changing food webs and resources in the Southern Ocean. And that's reflected in some recent work published just this year by Louis Hoekstedt and colleagues, some modeling work looking at crab-eater seal foraging ranges. And again, it appears they're likely to disappear from the northern areas of the Antarctic Peninsula and move further south along the Western Antarctic Peninsula. Of course, the alternative is, as they raise very nicely in their work published in Nature Climate Change, is that the seals themselves may, instead of moving, actually switch diet. And that would be a significant food web change. Alongside these changes, marine changes on the peninsula, we also, of course, see changes to penguin populations. Some of these are now very well recognized. This is some work done by Mike Dunn and colleagues with declines in Adelie penguin abundances, a little less of a decline in chinstrap penguin abundances, and an increase in gentoo penguins. Around the rest of the continent, things are not the same. They're a little more complicated also by the fact that we don't have long time series for certain areas, but that's being remedied, of course, by satellite-based observations and work by Heather Lynch, Peter Fretwell, and others is showing just how satellite observations can be used to understand populations in general. There is, of course, a great deal of stochasticity to these populations, and again, that draws attention to the fact that attributing change is not always straightforward. It's not only along the peninsula that we're seeing declines in penguin abundances. This is work by Henri Weimskirch, Peter Ryan and colleagues, and in fact, Peter and colleagues took these photographs that are being shown here. This is work on Île-aux-Cochons in the French subantarctic islands of the Crozet archipelago. And this is the largest king penguin colony on Earth. And it's shown significant decline between the 1980s and the 2015s. So we're seeing penguin abundance changes throughout the region. If we think about terrestrial systems, one of course immediately remembers that the Southern Ocean is a huge ocean. Terrestrial systems in Antarctica cover an enormous area too, a very large continent. And they're quite diverse. So although a lot of the continent is covered by ice and snow, just a few percentage points are ice-free areas. Some of those ice-free areas are large, and often they're very different. So one might compare, for example, the nutrient-poor dry valleys in the McMurdo Dry Valleys area to the more orthogenogenic or nutrient-enriched from guano soils and conditions along the Antarctic Peninsula, for example. And in some cases, there's almost no free water, while in others, there's plenty of free water, especially in the summer. And that's reflected by this diversity of ecoregions across Antarctica. And it's important because generalization is not the same across different parts of the continent. The peninsula, as we've just heard, is getting warmer and a little wetter. And around East Antarctica, there's windier and drier conditions. And that drives very different changes in biological responses. One of the first of these that's pretty clear is the rapid response shown on the Antarctic Peninsula. And this is work that's being done by Matthew Amesbury and colleagues, showing that there have been tremendous increases in microbial productivity, in the growth rate of mosses, and in accumulation rate. And just take note of the fact that there seems to be this threshold around about the 1950s where things have changed tremendously. And there, for those of you who've been following the Anthropocene literature and some definitions of the Anthropocene, one will realize that this coincides very nicely with the kind of 1950s time period when the Anthropocene really got underway. And I think it's important to realize these changes are likely to continue, and we're likely to see a very different Antarctic Peninsula emerge over the following years. In East Antarctica, Sharon Robinson and colleagues from the University of Wollongong here in Australia have been doing some work just showing how drying is affecting biological communities, and in this case, communities of mosses. So there's a species known as Schistidium antarctici. It's an Antarctic specialist. It really enjoys wet conditions, but over the years, conditions have been drying substantially, and this Antarctic specialist has been replaced by indigenous species to the Antarctic, 2 moss species, but they're globally common too. So whereas we have had a specialist community really dominated by this Antarctic specialist, we're now seeing moss communities have more moribund individuals, so there's greater mortality, and being replaced by individuals that tend to be more widespread and common. And this has continued into the most recent period. And of course, only through long-term research have Sharon and her colleagues been able to demonstrate this quite significant change. So these are changes that are taking place to the indigenous communities in the region. Importantly, that's not the only change that we're facing. There's been an increasing number of records of non-indigenous species. Those are species indigenous to other continents that have shown up in Antarctica, most likely as a consequence of direct human transport. There's plants such as annual bluegrass on the peninsula, There are invertebrates such as springtails that are on Deception Island and other islands. And the expectation is that this is going to continue and become more prevalent into the future. So we expect that not only from cold climate species shown down below here, that we expect larger numbers on the peninsula especially, but we might also expect some of the world's worst invasive species to show up. And Poa annua, certainly in an Antarctic context, this annual bluegrass is a very widely distributed species. In some senses, we can be thinking that we're starting to turn parts of the Antarctic anyway into just a member of global suburbia, because I guess any of you could walk out of your houses wherever you are and look around within a few meters, not even breaking your lockdown restrictions in Melbourne, and find Poa annua very close by. So what are the consequences of these changes? Of course, there's large habitat changes. The images you see before you are from the Gulbranson Lake and the Noimai Glacier on South Georgian Island in the Scotia Arc. In 1994, I took the images to the left. Of course, they scanned because it was on film then. And 20 years later, almost to the day, I took the images on the right, and you can see very clearly the disappearance of a large section of the Noimai Glacier and Gulbranson Lake. And more generally, this means that we're going to see new habitats opening up and conditions changing substantially for species. Some work in the marine region done and published this year by Mark Hindell and colleagues has drawn a great deal of attention to this using a fantastic compilation of Antarctic tracking data that was facilitated through SCAR. And if you look at these blue areas to your right, these are areas of ecological significance for birds, seals, and whales. Here in the Scotia Arc on the left-hand side and across on the South Indian Ocean Province Islands on the right-hand side. And the rings and circles and red and orange squares you see are either extant, existing, or proposed marine protected areas. Importantly in this slide, you can see that future projections are that there'll be loss of area and gain in the north and gain of area to the south, and then some movement around the Antarctic continent itself. And from a policy perspective, this raises the interesting question that some of the wins with marine protected areas, for example, the Ross Sea region marine protected area, took a lot of negotiation and a lot of effort actually to get over the line, to be successful. And we can expect some changes here that will change the properties of those marine protected areas. From a policy perspective, that doesn't mean we should give up. In fact, that's entirely the wrong approach. Rather, we should think that the marine protected area network has to be expanded to take into consideration these future changes that the modeling suggests will occur and will occur over the next 100 years or so. And the benefits from expanding the marine protected area network come not only from, of course, looking after the biodiversity for which we're responsible and which we've agreed to do through several Antarctic Treaty System agreements, but in fact, that also means the resources that we're interested in have somewhere to go, somewhere where they are not exploited, and therefore the benefits for limited take are quite obvious and have been demonstrated elsewhere. It's not only changing climates though that are important, but of course human activity has changed substantially across the Antarctic continent in the more or less 200 years that we've been either exploiting or exploring or studying it. And this is quite important for the future of what we might expect biodiversity to do because of colonizations. So human activity really is very substantial. And as a consequence, both of changing climates and that human activity, we can expect threats to the ecosystems really to increase as a consequence of introductions of new species. And not only those from the subantarctic, and please remember that Latin America has a very large subantarctic region in Tierra del Fuego, Patagonia in Chile and Argentina, but also from elsewhere. We have an expectation that many species will actually be able to colonize the area. What does this mean? Of course, many people say, when I speak to them about invertebrate species colonizations, they say, so what? And one of the things I'd like to draw your attention to is some work on rodents that have colonized the subantarctic islands. House mice arrived on Marion Island of the Prince Edward Island archipelago, probably with sealers in the 1800s. But we know from some long-term research on the island that the consequence of changing climates is that mouse densities have increased. They're able to breed earlier because it's warmer and a bit drier. Their densities have increased huge amounts, and that has led to a decimation of the invertebrate prey. And again, people say, well, so what if we lose, 3 orders of magnitude of, say, an indigenous weevil? And my answer is that would be like saying, so what if we go from 100,000 penguins to 10 of a particular species? And even that sometimes doesn't have that much impact. We are losing species and changing ecosystems. But of course, if you think back to the theory that I was talking about, the theory of Wieland's, and of course with significant selection imposed on mice, they have to switch to something else if they run out of food. And immediately we see impacts now, and quite surprising ones, on other organisms. So this is work by Peter Ryan, Ben Dilley, Stefan Schoonby, who's responsible for many of these pictures, and colleagues, showing that mice have switched to attacking albatross chicks and albatross adults on these islands because they've effectively run out of resources on these islands. And we may have had huge successes with our policy to reduce illegal, unregulated fishing, and those may be undone by these significant impacts of invasive species on the nesting areas of these birds. Of course, this matters more broadly too, and we should ask ourselves always, what does it matter to those that are not working in the Antarctic? Why should they care about it? Why is it important? And from that perspective, the most significant aspect from my view anyway, is that we've actually signed up to a global set of goals. These are the Sustainable Development Goals. We have, as society, promised ourselves that we will look to taking climate action, to looking after all life below water, all life on land. We recognize that those 3 goals actually are going to influence every one of the other Sustainable Development Goals. From an Antarctic context, I think that we should recognize that what we do elsewhere in the planet has an enormous effect on Antarctica and vice versa, as our previous 2 speakers showed. But conservation is just as important for the region as it is for elsewhere if we're actually to address these goals. So the interactions are not just limited to those of the physical world, but also to those of how we actually look after the environments that we have agreed to look after through our various agreements. And some might remark that the UN Sustainable Development Goals and the Antarctic Treaty System are a little different. But of course, I would remind everyone that there are very explicit statements in the Antarctic Treaty itself that we will seek to actually have good interactions between those. And I think it's essential into the future. People often say, well, what to do? And I like to start with what not to do. I think there's good evidence now that adding another experiment to already 2 major experiments underway on our planet would not be a very good idea. And those 2 major experiments are, of course, the climate crisis and our current pandemic. I don't think that adding solar radiation management would be a very good one, especially since we have some very clear indications, and that was set out very nicely by Valérie Masson-Delmotte in her opening plenary, that we know exactly what it is we have to do to get the trouble that we're facing at least better under control. Nick pointed out we already committed to some of it, but we have options to reduce this into the future. And these are made very clear by the IPCC's reports. I'd like to then start drawing this presentation to a close by saying we have quite a good idea of what to expect in the ecosystems of the Southern Ocean and the Antarctic more generally. We know, for example, that we're likely to see changing distributions of benthos as a consequence of changes in sea ice and ice shelves. We know that we've seen particular changes in species such as work showing changes in wandering albatross size and breeding success. We know about invasive species. We essentially have a very good idea of what's happening and what we might expect, although there's a great deal of uncertainty and the research is required to continue to reduce that uncertainty. But we're often quite stunned by the fact that we don't seem to, as a society anyway, and I'm speaking very general terms here, take sufficient action and action that's fast enough. So there is, of course, plenty of action that's been taken. Nick and Valerie both mentioned NDCs. We know that there's a great deal of interest in getting on top of this problem, and we see it from business too, and we see local changes through the actions taken by city councils or regional councils in cases where governments are too slow to respond. But it still has been asked several times, and in fact, that's part of the questions that Nancy, Flo and Cred asked us, is why do we see such resistance elsewhere? And work that Cassandra Brooks and I have been doing just recently partly addresses this. So if you look to the left-hand side of the figure here, this is a very typical 2x2 matrix you might see out of somewhere like Harvard Executive Education, where we have reliable knowledge on the x-axis, and this is in John Zimon's terms. In other words, we agree that we have the evidence for the way the world works, whichever part of the world you're thinking about, and that might be low or it might be very high. And then we have a second orthogonal axis, which is policy appetite for evidence. In other words, to what extent do policymakers really want to use our evidence? Whether we present it in compelling ways, simple ways, easy ways to understand or not, but just what is their appetite for that evidence? And of course, ideally, we really want to be in this top box here, where we take evidence-based decisions, we have effective policy, we have engaged, informed dialogue, we have research funded in priority areas. Often we find ourselves on the top left-hand side, but this top right-hand side is really where we want to be. Too often, though, we see society being forced downwards into this bottom right-hand side box, which is really a position we don't want to be in at all. And the question might be is why do we see this happening so much? And Cassandra and I thought that it's important to recognize with some of these 2x2 approaches that often, as is the case with natural systems, there's an underlying cause. And we think it has to do with an asymmetry, what we might call a societal science-mindedness or even just an education asymmetry. And that is that it takes a long time to gain an appreciation for evidence and what evidence actually means, and an appreciation for expertise and the importance of expertise in society. You could think of this curve on very long time scales, starting at about the dark ages here and going up to where we find ourselves now. But the loss is like hysteresis in engineering terms, and that is that we have a very slow loss initially, and then it plummets quite quickly. So once one's down on this curve, one can't go back up it very quickly. It takes a long time to regain it. And all this tells us is that we really want to stop things somewhere along here and make sure that we have very good education. And it's something that in many countries actually hasn't been done. So if you look at responses to the climate crisis, or you look at responses to the current coronavirus pandemic, and you look at the responses of different countries, then you might well be able to position them on different parts of this 2x2 matrix and have a think about what the result is of the policies they've adopted and why it's so important to adopt policies that actually keep us very well aware of the importance of science in society. I would like to, in this respect, just raise a small shout out to Nick Gollidge, Tim Nash and colleagues from New Zealand who were recognized for their work in Antarctica by the Prime Minister's Science Prize in New Zealand. And I think from an Australian perspective, we look across what's known conveniently as the ditch and think it would be very nice, at least from a Melbourne perspective, to be sitting in New Zealand just at the moment, rather necessarily than being locked into our houses. So with that, I'd like to thank all of the colleagues who've been extremely generous with their work, with their time and with their discussions. We recognize also the outlets that have published all our work, and I've taken some images from a variety of sources, and I'd like to recognize those, and especially all the people that contribute to the IPCC special reports. Finally, just a thanks to those who funded me, the Australian government through the Australian Research Council and the Australian Antarctic Program, Monash University where I work, my lab group that's very careful about looking through all of my presentations, and then just to recognize we have this new special research initiative coming, as Crid mentioned, and we will provide you with some more information about that into the future. So thank you very much, Crid.
Thank you, Stephen. That was a wonderful talk, very interesting. And we're flooded with questions. And so I'd just like to remind the audience that we are going to have a general question and answer session. So at the moment, we're just going to direct 1 or 2 questions to individual speakers, and then I'll open, we'll have a few questions that we've prepared for the panelists and then open it to the floor. So we hopefully will get to your question, but apologies if we don't. So Stephen, you touched on the interactions of Antarctic ecosystems with the rest of the world. And I wonder if you could expand on some of those interactions. There's a good question here asking, do impacts on the Southern Ocean ecosystem have downstream impacts on ecosystems elsewhere?
Well, Cred, I think the short answer to that is, and the simple answer is yes. I mean, the magnitude of those may of course be a little different, but we know, for example, if you simply think of pelagic predators, they don't spend all their time only in Antarctica. They move about to other areas. So the magnitude is quite important to understand. From a human resources perspective, what fascinates me is the fact that fisheries elsewhere have, on average, not fared very well. There are a few that are okay, but the rest of them have been quite depleted. So what happens in Antarctica actually is something that we'll have to look out for in terms of how the rest of the world's fishery status will then impact in Antarctica, and in turn what that might mean for fisheries elsewhere. So I think we don't have as good an understanding of this problem as we should. But I would say that the short and simple answer is yes, but the magnitude is something we need to think about.
Great, thank you, Stephen. So I think now we'll move directly to the broader panel discussion. So if all the speakers could rejoin us, please. And I'll start with a general question for you all. What do you see as the main challenges or key priorities for the Antarctic research community over the coming decade?
I could jump in from an ocean perspective. I think from observing the Southern Ocean perspective, we're entering yet another new era, which is exciting. Our ability to observe the oceans under the ice is improving, and our ability to measure what's happening in the deep ocean through deep Argo we're finally able to do that on a sustained and continuous way. So that means there's an opportunity to understand how the Southern Ocean works, particularly in the poorly observed areas under ice in winter, that are crucial to how the ocean then interacts with the marine ecosystem of Antarctica and the sea ice and ice sheets. So in terms of things we need to know, I think probably the most important from an ocean perspective in terms of societal impact is what's going to control how much ocean heat reaches ice shelves and drives basal melt, as Nick has explained. The other changes are also important. There's the potential for feedbacks. If the Southern Ocean becomes less effective at storing heat and carbon dioxide, for example, that could lead to feedbacks that could accelerate climate change, or the reverse, if they become more efficient. But probably the most immediate societal impact of Southern Ocean change would be the commitments that we make to ongoing sea level rise in the future.
Okay, so I can jump in on the ice sheet perspective. I mean, you're talking about challenges going forward. I mean, as I sort of alluded to in the slides, we still have a lot of work to do in the ice sheet modeling community in terms of not just making sure that the input data, the forcings we're using are the most appropriate, but in understanding how we translate those into ice sheet changes. And I think there's a tendency to sort of get a bit sort of blinded by some of the new whiz-bang theories that come out, and all these sort of special things that could or couldn't happen. But fundamentally, I think we need to kind of stay the course, stick with what we know, and just say, well, look, let's try and make sure that the models we're using actually capture the fundamental processes as well as we can before we start adding processes that we don't really understand. I think there's a lot of work to be done there. And part of that work actually comes down to having the observational data that we can use to check that the models are doing the right thing. And this works over many timeframes. We need observational data over sort of annual to decadal timeframes for the recent past, but we need to be using the paleo-environmental data that exists that goes back centuries and millennia. We need to be using ice core data a lot more. We need to be using the geological record a lot more. We need to be using this and really learning from it how the ice sheet has behaved in the past, and how we can actually use this to more rigorously control our models. And I think if we can do that and focus on the fundamental physics then I think we'll be in better shape, and hopefully we'll see a bit more agreement between models.
From a biological perspective, I'd say there are a few things that are really important to understand. One is the trajectory of important populations, so those that support the ecosystems in the Southern Ocean. I think that there's an interaction here with the physical sciences too. So much of the biological attribution is actually dependent on work underway in the physical science for attribution too, as to what the causes are. And I think it's important that those interactions are very much better understood. One of the things that is a real challenge, and I think very important into the future, is understanding what the implications of these single species changes that we know about will be for food webs generally. So we've done a lot of food web work in the past. There's some ongoing now, but I think food web studies showing how things have been changing and what the consequences will be are quite important. And going back to the question of, what does it mean for the rest of the planet? I think it's important also for us to understand that the Southern Ocean and its species and ecosystems are actually a key component of the world. So if we said we were going to lose European lynx, or we were going to lose rhinoceros, or we were going to lose some of those other species, there'd be a huge outcry on the fact that we're not looking after our ecosystems and species. And the same is for the Antarctic. So some recent work we did showed that if you take a global perspective anyway, the whole of the Antarctica is a wilderness. And we'll end up losing it if we're not careful. We'll turn it into something that looks a bit like a global suburbia with lots of invasive species and very little else that's special about the continent. So I think that those are elements that we need to think about a great deal, and how we may actually address them. It strikes me that at the moment we're actually busy with one of the largest biosecurity protocols ever for the Antarctic, since everybody wants to stop COVID-19 getting into the Antarctic. And that's just a biosecurity question. So there's some lessons to be learned from national Antarctic programs about biosecurity general, given all the efforts that are being gone to undertake that work now.
This might be a good point to leverage into our next question, which nicely aligns from that. And that is, can the COVID pandemic be a trigger for renewed and enhanced engagement to mitigation climate change? As governments invest trillions of dollars, of course, now into their COVID-struck economies, how can we support policymakers best to give them timely advice and avoid, dangerous legacy?
Well, I'll give that a go first. I think Steve was looking there too. I just want to draw your attention back to Valérie Masson-Delmotte's presentation. So we actually have very good advice in terms of what the alternatives will be of the various scenarios we pick, provided by the IPCC and the tens of thousands of scientists that actually have been involved in the IPCC's reports, especially the special report on global warming of 1.5 degrees Celsius and on oceans and cryosphere in a changing climate. And I think the advice there is very clear to us, even though there's no recommendations, as Valerie pointed out. But if we look at the options, then from a policymaker perspective, we can say, if you seek to rebuild your economy in the way that it just was, using essentially greenhouse gas emissions as a means to drive it, then we will make no change whatsoever. And that's true also for what just drove the most recent pandemic. So from an environmental change perspective, if we wish to continue with greenhouse gas emissions to the extent we have, if we don't increase our ambitions under the NDCs, if we continue to remove habitat, if we continue to trade in wildlife for food as we have, then the expectation is we're just going to have more of this, not less. And I think it's, I don't really want to imagine what a coronavirus crisis might be under a world that's 3 or 4 degrees warmer on average, which means that actually on some continents like Australia, we'll have huge bushfires, as Neroli Abrams pointed out. So we'll be dealing with the economic consequences of huge bushfires and a coronavirus pandemic and the next one as it comes along. And I think that those messages are very clear now. The question, of course, is how do we get it across to the voting public? That's, I think, in many cases, much more important than some of the politicians that are there, because it's in many, many circumstances actually our neighbors and our friends and those around us that are most significant, since they're the ones that end up putting the politicians into power in the first place.
I guess one way to think about this is it's almost obscene to say it, but what the trauma of the pandemic has given us is an opportunity to reset our economies and our ways of living that are more compatible with the planetary boundaries. And so, as you say, governments will be investing trillions of dollars to rebuild economies that have been broken by COVID-19. And if we did that in a sensible way, we could secure ourselves. We have an opportunity to secure ourselves a more sustainable and livable future. Of course, the flip side of that is that the disruption and true trauma of the scale of the pandemic means that it will be difficult to get attention paid to other things other than how do we get a life back that we can live with as rapidly as possible? How can we stop the destruction? How can we stop the deaths? How can we get people back to work? So I'm by nature optimistic, and I would like to believe that one impact related to some of what Stephen covered at the end of his talk, the lack of action on, there are some parallels between COVID and the response to COVID-19 and the response to climate change. Some things like that the impact of the virus will be greater on the poor, whether it's poor countries or poor communities within wealthier countries. The disadvantaged will bear the brunt, and the same is true for climate change. It's also true from COVID that the science was pretty good, that if you believed the scientists and acted on the basis of the best evidence from epidemiologists of how this might pan out, and you built your policies on that evidence, you dealt with the virus much more successfully than those that ignored the evidence. The problem with climate change is that we're more affected by the global response. We now need the global community to recognize the science is pretty clear. We know what we need to do, just as the science was clear in many ways for COVID. In both cases, there are large uncertainties remaining, but there's sufficient information to act. And so we could, in an optimistic view, carry that new appreciation for evidence-based policy, put us in the upper right-hand box of Stephen's diagram, and plan a new future that is sustainable and fits within the planet we've been given.
Yeah, I would just pick up on both of the Steves and the comments made there. I think one of the things about the COVID pandemic is that it's really kind of brought it home that we need evidence-based decision-making at the highest levels. And I think if we can kind of use the momentum that's been developed there over the last sort of 6 months with the pandemic, then we're in pretty good shape to kind of hammer that message home that really any policies that are made need to be based on the best available evidence. And some countries are good at this, others obviously less so. Very much like the 2x2 matrix that Stephen put up there. If we can kind of try and push more governments towards that upper right box in that matrix, then that's got to be a good thing. One thing that I saw on Twitter the other day was somebody saying, the thing about COVID is it's made people realize that we live in a society, not an economy. And it's a simplification, but it's kind of a nice way of thinking about it. We rely on the economy, obviously, to keep us all alive and well and happy. But fundamentally, we live in a society. We are a societal population. We live in a community, and the people around us are important. So that applies whether it's a pandemic or a global climate crisis. So I think that's something that's worth remembering as well.
Okay, We have another question that actually is interesting, has some links with actually the logical answer from this question. So then how can we project our global projection to local realities, to communities? How can we translate actually those projections? I think it's definitely linked to what we have been observing with COVID-19.
Okay, well, I can jump straight in there on the ice sheet side of things because so much of what we do is very much focused on sea level rise, and of course the impacts there are very sort of community specific, and so that's a very obvious way that we can kind of bring the message home. And we're doing work in New Zealand through a government-funded research program to basically try and downscale those global projections and regionalize them using the local geological data that we have, the best available evidence for vertical land motion, changes in actually across quite small areas, to try and really give specific answers to communities as to whether they're safe from sea level rise within the next sort of few decades, or whether they're actually going to be more affected than maybe the global mean. So there's plenty that can be done in that space. But of course, the flip side of it is that regardless of that regionalization aspect, we still have things that affect all of our communities, even if we don't live by the sea. And that basically comes through the insurance and the reinsurance system. So there are economic impacts that will be felt by every community, even if you live at the top of a mountain. So always worth remembering that.
In terms of climate change more generally, I think increasingly the impacts of climate change are being felt locally. For those who lived through Australia's fire season, for example, it was very clear that things were different than they've been in the past, and that a warmer, drier world is one that's going to be very uncomfortable and dangerous and costly. That message of that the impacts are local, I think is getting through. One reflection of that is that while we might be concerned by the slow rate at which some nations have responded to climate policy, if you look at the commitments that were made in Paris, the commitments from individual industries or local governments or cities, states, people are feeling it on the ground, and so they're the ones that are ready to act. And so we may actually build a response from the bottom up rather than the top down.
Okay, thank you all. And now I'm going to take some questions from the audience, and there's quite a lot here and I don't think we'll get through them all. So apologies again if you've asked a question that we don't get to. But I'd like to start with one which I think is aimed mainly at Stephen Chown as the more ecological representative. And this is a question from an anonymous person in the audience asking, we generally consider the impacts of the physical environment on ecophysiology and biodiversity, but can we take the opposite perspective? Are there plans to investigate how changes in biodiversity and organism reactions to climate change might influence the physical environment? Particularly, for example, how microbes and algae in sea ice might influence sea ice and ice sheets.
Yes, thanks, Trent. I think the first point I'd like to make is that in a deep time sense, we live in a biologically constructed world. So I can just think of the concentration of oxygen in the atmosphere over deep time and how that changed and what the consequences then were for all life and the physical environment. I'm also reminded of a paper that came out a few years ago showing the response, or at least as far as paleoclimatologists could understand, the response in the Arctic Ocean to the situation where a water fern, I think by the name of Azolla, actually came in and may have been responsible for a huge amount of CO2 drawdown in the area. And that was driven by some freshening of water. And again, one can also think of the changes in reflectivity or albedo and the extent to which this may drive local dynamics. So from my perspective, yes, of course, if you think about drawdown of carbon and you think about the way the environment is constructed, there is a reciprocal interaction on Earth. I just don't think that we understand some of that reciprocity as well as we should. And in the Antarctic, there's some very specific things going on in terrestrial communities. I'm not going to go into the detail here, that I think will have a huge impact. One tends to think that in the dry valleys, for example, that there's not much going on there at all, but microbial systems are really quite extraordinary in those areas. And what the future is there is very difficult to discern. So the answer is, I think we haven't thought about it a lot in this region, but elsewhere it's very clear what's actually the case is. And so there is this reciprocal interaction between the physical and the living environments. I mean, that's the whole point of understanding the Earth as an Earth system, and all the climate models, of course, have to incorporate biological responses too. And I think that's pretty clear. I think more generally what's going to happen in some of the tropical regions is an important question in terms of deforestation and what the effects of that deforestation might be. Perhaps others know of further work, but that would be my initial response anyway.
Great. We also have another question from the audience who is asking, what are the key uncertainties that need to be addressed that we can give policymakers more accurate predictions? Where are sort of the key areas where we can make progress?
I guess maybe one point to make from the start is that we don't really need more information to act. The science has been pretty clear for a pretty long time that the consequences of continuing to emit high levels of greenhouse gases are things that we would like to avoid. And Nick has mentioned that there are thresholds that lie not very far ahead of us that would lead to fundamental shifts in the commit us to changes in sea level in particular that are then committed. We can't change our mind later on. So, it's in the nature of talks to highlight many of the uncertainties and the gaps. And I think a number of those have come through in the 3 talks that we've heard today. But we should keep in mind that we do know quite a bit. And in particular, we know enough that it's better to stay closer to a 1.5 degree C world than a 3, 4, or 5 degree C world. But from a, and I think the sea level, to take it home to the voting public and those and the policymakers that the public elects, the earlier discussion about local impacts is important. We need to make clear that the impacts of climate change will be felt locally, and they will impact everything about how we live, just as the virus is affecting everything about how we live. And sea level, as Nick mentioned, is something that brings it home to many coastal states at least, but although the impacts will extend beyond those living on the coastal fringe. Local councils are already wrestling with the idea of what do we do when houses start falling in the water due to coastal erosion and rising sea levels? Where should we allow development? What's the, how do we deal with people that can no longer get their houses insured? Bushfire or even health risks independent of the pandemic are things that are starting to become more and more evident. And so I think the more local it is and the more immediate it is, the more likely action is to be taken. And that's really probably the biggest difference between the virus and climate change is the timescale on which it's evolving.
Yes, I wanted to add to what Steve is saying, that those interactions are really important to drive home. So for example, we have, as Nerily pointed out, a picture in Australia anyway, on the southeastern side, of houses falling into the sea. And that was a picture followed shortly after a picture of actually whole communities being driven to the coast because the interior of the regions essentially in a firestorm that most of those who have a lot of experience indicated they'd never experienced before in decades of dealing with these questions. So we have a real interaction here because we have those two, and then followed on that is, of course, this global pandemic. So all of the rebuilding in those local communities that may have been based on a vibrant tourism industry has basically disappeared. And Steve's message is exactly right. We know what to do. More broadly, the policymakers, we've given them the evidence too. So, for example, we can say exactly, we have some uncertainty, but we can say that marine protected areas just aren't sufficient in the Southern Ocean to do their job. It's very straightforward. All the evidence is sitting in front of us. And we don't have to do too much work except to address some of the uncertainty. But the message is clear, and that is pay some more attention and get over the line with marine protected areas and those interterrestrial systems too. So I think it's, I agree with Steve, it's quite obvious in many cases what needs to be done, even though there is some uncertainty, and we now have very good tools for communicating that uncertainty clearly.
Yeah, I would echo all of those comments really, and I think the key thing that Stephen just mentioned there about the tools for communicating uncertainty, I think that's probably the key thing really. I mean, there's only so far you can go with improving models, and I think there's a sort of perception that somehow when all the models are perfect, we'll get rid of the uncertainty, and that's just not going to happen. In fact, we see a tendency towards the opposite, that actually the more models we use and the more of the parameter space that we explore, the wider that window of uncertainty gets. But the central tendency becomes more certain, right? So that's the key thing. We need to sort of find a way to communicate that more clearly. Policy makers they shouldn't be afraid of the uncertainties. They should just understand we need to sort of convey to them why the uncertainty is useful. You know, it's a bit like Donald Trump talking about the problem with the increased number of confirmed coronavirus cases was just because they were testing more. You know, if you don't look, you don't find the problem. So, you know, at least in the ice sheet model world, and I think also in the climate world, you know, we're probing the system as much as we can with different models and different implementations of those models. That gives us a more complete understanding of the system. And I think that is something that's a real strength. So maybe we just need to think about the language we use in communicating so that people don't hear the word uncertainty and think you don't know what you're talking about. They hear it as a more complete understanding of the system. So I think there's some work to do there on both our sides.
Thanks, Nick. So yeah, actually, I mean, if we try to summarize a bit what has been said, is in very few words, like the system is really interconnected. I mean, in the Southern Ocean, what will happen to Antarctica and what happens to ocean will at some point interplay together, and then it will impact on the ecosystem. And to some extent, we need to effectively understand better what will happen. So for that, we need to extend our observational networks, both for the past and for the present, to definitely put some efforts into the process that we definitely do not have any understanding, or very poor understanding actually. And unfortunately, those processes are the one that will determine the tipping point of the system, both in the oceans and in Antarctic ice sheet. So it's effectively everything is bit connected. And I definitely what can emerge from this discussion is effectively that the communication is something that we need to make more effective. To translate our findings in something that is definitely useful for policymakers, and effectively this problem of rates of quantities that could be a rate of sea level change, but rates of ocean uptakes or rate of species migrations. The rate is definitely a delicate variable to communicate to the policymakers, and the fact that it's highly depending on the scenarios effectively make it a bit worse for this kind of communication. So I would like, with Nancy and Creed, to thank all the speakers, Steve, Nick, and Stephen, for their very great talk and a very effective discussion for this panel. Would like to thank the audience for attending the mini symposium and their active participation to the discussion through the question and answer. And finally, we would like to acknowledge SCAR Online Organizing Committee and technical staff for all the excellent organizations of all these events. Then I would like to remind you that next sessions are in perhaps something like 10, 11 hours. It will be a poster session, and then will be followed by 2 plenary sessions, the first one by Juliana Viana and the next one by Daniela Liget. So thank you very much, and have a nice day or night or afternoon.
See you all.